Well, if I don't wear socks, my feet get a little clammy and like start to kind of like sweat a little bit. I guess I'm comfortable. I'm a sock maniac. I got like 100 pairs of socks. Go through them like crazy. Most underrated clothing item, socks for sure. Socks and hats, I'd say. All right. Yo, what's gravy? What's cracking? What's groovy? Hello, hello, hello. Welcome one, welcome all. Welcome in. I'm your captain speaking. Welcome back into the stream. This is the midday matinee. Alright. Let's get this show on the road. I need to go to there. Start Twitch. Pop it out. Oh, come on. Doing that thing again. There we go. Bow. All right. Cool. What's up, Maddie? What's up, Mahan? Yeah, covering up them dogs. No dogs on stream. This ain't that kind of stream. All right, you guys, what's going on? Hope you're having a wonderful day so far. Welcome back in to the stream. My name is Michael. Introduction, I'm 26 years old. Got a degree in human biology and minor in chemistry, and I work as a formulation chemist where I make biological controls. I've been teaching myself how to code for a little over 1 year now, a year and a half about, as I have been learning various things like Python, algorithms, data structures, hardware, getting down in there, hopefully, soon. All right, you guys. So the midday matinee stream, we're just going to be reading for, I'd say, probably about an hour or so. In Introduction to Algorithms, 4th edition. So let's go ahead and pause the tunes. Let's get a intro for the YouTube video that I'm going to be chopping up. And we'll get going here. Yep. You guys know the drill. I need to pull up chat here. Here we go. All right, let's get a recording going and let's get this show started. All right, hello everybody, welcome back in. My name is Michael, and thanks so much for joining me again today. We're going to be jumping back into Introduction to Algorithms, CLRS, 4th edition, more specifically Chapter 4 today. We're going to be reading this one. Let's get started. Chapter 4. Chapter 4 is all about divide and conquer. It is a little bit of a lengthy one, so I'm probably going to chop this up into a few different streams, probably about 2 parts, potentially 3, but here we go. All right, let's get into this. Like always, you can see my notes are on the right side of my screen. You can access them on my GitHub, which is in the description of the video. All right. Let's get going here. Where are we? Chapter 3, Chapter 4. Here we go. We're almost at 100, page 100, almost a tenth of the way through. Moving along quite nicely. All right. You can take a drink here. Got a wet whistle. Ah. Okay, you guys, let me know how the audio is, if you like, if it's all right, but let's get started here. If my screen stops recording for some reason or like it freezes, let me know. That happened in chapter 2. For some reason, I had to go back through and actually paste the screenshots of the pages back over for the video. Also, I am chopping these up to condensed versions such that as they are like audio books, where I am just reading fluently with no breaks and no pauses in between. So if you would like to check those out in a more condensed format, please do so. It's kind of a great way to have them on in the background. Let's say if you're stuck in traffic or something like that, just to reiterate the content and solidify it over again. It's really nice, and it's only about 25 minutes to 50 minutes of just kind of reading and going over stuff. Cool. Let's get started. Chapter 4. Our Corman Introduction to Algorithms, 4th edition. Chapter 4. Divide and Conquer. The divide and conquer method is a powerful strategy for designing asymptotically efficient algorithms. We saw an example. Okay, not off to a bad start. We saw an example of divide and conquer in section 2.3.1 when learning about merge sort. In this chapter, we'll explore applications of the divide and conquer method and acquire valuable mathematical tools that you can use to solve the recurrences that arise when analyzing divide and conquer algorithms. Recall that for divide and conquer, you solve a given problem instance recursively. If the problem is small enough, the base case, you just solve it directly without recursing. Otherwise, the recursive case, you perform 3 characteristic steps. Divide the problem into one or more subproblems that are smaller instances of the same problem. Conquer the subproblems by solving them recursively. Combine the subproblem solutions to form a solution to the original problem. A divide and conquer algorithm breaks down a large problem into subproblems, which themselves may be broken down into even smaller subproblems, and so forth. The recursion bottoms out when it reaches a base case and the subproblem is small enough to solve directly without further recursing. Recurrences. To analyze recursive divide and conquer algorithms, we'll need some mathematical tools. A recurrence is an equation that describes a function in terms of its value on other typically smaller arguments. Recurrences go hand in hand with the divide and conquer method because they give us a natural way to characterize the running times of recursive algorithms mathematically. You saw an example of a recurrence in section 2.3.2 when we analyzed the worst case running time of merge sort. Okay, let's quickly jot down some notes here. Conquer. So let's chop down some notes here really quickly. So we have a few things, right? For one, we have divide and conquer, right? A powerful strategy for designing asymptotically efficient algorithms. Kind of a broad definition, but it's okay. Let's kind of break it down into 3 steps. Okay. Why does that not work? Interesting. I can't tab in. I thought I could. Why is this nested not work? Do I have to be like... No. Interesting. Whatever. Divide the problem into one or more subproblems that are smaller instances of the same problem. That's a good, okay, right? Number 2, conquer the subproblems by solving them recursively. Perfect. And then number 3, combine the subproblem's solutions to form a solution to the original problem. So we have, let's then talk about here really quickly, we have a base case and a recursive case. The base case, you just solve it directly without recursing. When the problem is small enough, so the base case is like the smallest possible problem to solve, or like the most broken down, the smallest form of the problem to solve at hand. I don't know, is that a good way of saying it? Recursive case, operations needed continue until because problem is still too large and needs to be broken down further to reach a base case. Something like this. Let me give the almighty orb this guy here. That's a solid start to capture the essence. A base case, the simplest problem instance of the problem that can be solved directly without further recursion, the stop condition. Okay. Yeah, that's a better way of saying what we were saying. With a recursive case, the step where the problem is reduced into smaller subproblems of the same type, moving it closer to the base case. Yeah. Cool. Hey, how's it going? I'm mainly doing this in Python for the moment, but expanding out into hopefully, probably, I think C, potentially C++ soon on the channel. Soon. We're not the type to rush though here. We like to dot our I's and cross our T's. Okay, let's keep on going. Did we read this already? Recurrences. To analyze recursive divide and conquer algorithms, we'll need some mathematical tools. A recurrence is an equation that describes a function in terms of its value on other, typically smaller, we already read this part. So then let me talk about here really quickly then a recurrence, an equation that describes a function in terms of its value on other, typically smaller arguments. Okay, 77. For the divide and conquer matrix multiplication algorithms presented in section 4.1 and 4.2, we'll derive recurrences that describe their worst case running times. To understand why these two divide and conquer algorithms perform the way they do, you'll need to learn how to solve the recurrences that describe their running times. Section 4.3 through 4.7 teach several methods for solving recurrences. These sections also explore the mathematics behind recurrences, which can give you strong intuition for designing your own divide and conquer algorithms. We want to get to the algorithms as soon as possible. So let's just cover a few recurrence basics now, and then we'll look more deeply at recurrences, especially how to solve them, after we see the matrix multiplication examples. The general form of a recurrence is an equation or inequality that describes a function over the integers or reals using the function itself. It contains two or more cases depending on the argument. If a case involves the recurrence invocation, the function on different, usually smaller inputs is a recursive case. If a case does not involve a recursive invocation, it is a base case. There may be a 0, 1, or many functions that satisfy the statement of the recurrence. The recurrence is well defined if there is at least one function that satisfies it, and all defined and ill-defined otherwise. Okay, all right, this is talking about recursion here. Algorithmic recurrences. We'll be particularly interested in recurrences that describe the running times of the divide and conquer algorithms. A recurrence, T of n, is algorithmic if for every sufficiently large threshold constant n naught, that is greater than 0, the following two properties hold. For all values that are less than that initial n naught, we have some recurrence that is constant. For all values of n that are greater than or equal to that initial n naught, every path of recursion terminates in a base case within a finite number of recursive invocations. Similar to how we sometimes abuse asymptotic notation, see page 60, when a function is not defined for all arguments, we understand that this definition is constrained to values of n for which T of n is defined. Why would a recurrence T of n that represents a correct divide and conquer algorithm's worst case running time satisfy these properties for all sufficiently large threshold constants? The first property says that there exist constants C1, C2 such that 0 is less than C1, which is less than or equal to the recurrence T sub n, which is less than or equal to C of 2, for all n values that are less than that initial n naught. For every legal input, the algorithm must output the solution to the problem it's solving in finite time. See section 1.1. Thus, we can let C1 be the minimum amount of time to call and return from a procedure, which must be positive because machine instructions need to be executed to invoke a procedure. The running time of the algorithm may not be defined for some values of n if there are no legal inputs of that size, but it must be defined for at least one, or else the algorithm doesn't solve any problem. Thus, we can let C of 2 be the algorithm's maximum running time on any input size of n, which is less than n naught, where n naught is the sufficiently large value that the algorithm solves at least one problem of size less than n naught. The maximum is well defined since there are at most a finite number of inputs of size less than n naught, and there is at least one if n naught is sufficiently large. Consequently, the recurrence T of n satisfies the first property. If the second property fails to hold for T of n, then the algorithm isn't correct because it would end up in an infinite recursive loop or otherwise fail to compute a solution. Thus, it stands to reason that a recurrence for the worst case running time of the correct divide and conquer algorithm would be algorithmic. Okay, that was a lot of kind of information and a lot of kind of a little bit of math behind it, but it kind of just talked about how in a recursive call you reach there's some values of n that we talked about in the previous sections, where you reach some value of n, and that's where you would start invoking recursive calls for every value greater than that starting place. Now that place could be 0, or it could be 100, or it could be 1,000,000, wherever that n naught starts that is sufficiently large enough for this algorithm to actually start. Now what it's also saying is that for any n values that are less than that initial value to kind of kickstart the recurrences, you have theta of 1 constant operations. So I'm going to quickly just take this here. And I'm going to throw it in here. I'm going to be like, so my interpretation of this section is that when we're talking about recurrence algorithms and some value of input n, we have some value n naught, which is a sufficiently large value to where we kind of quote unquote kickstart recurrences. And any value that is less than that n naught value, invoke a base case on the algorithm, thus creating a theta of 1 constant operation. Right? Is that kind of what's going on here? What is it? Can you give me more detail about that theta of 1 for n that are less than that n naught? Yes, you're reading it correctly and your interpretation is on the right track. Let me unpack this carefully. The role of n sub 0. When we define a recurrence for a divide and conquer algorithm, we need a cutoff point between inputs that are considered small enough to solve directly with the base case and inputs that still require recursive decomposition. That the cutoff is what you're calling n naught. If n is less than n naught, the problem size is small enough that the algorithm doesn't recurse anymore. Instead, it solves the instance in a bounded constant amount of work. If n is greater than n naught or equal to it, the recurrence applies, splitting it into subproblems recursively. So n sub 0 isn't one magical number. Any sufficiently large threshold could work. It's a way of formalizing eventually the recursion bottoms out in a base case. So y theta of 1 for n sub 0 is less than n sub 0. When the problem size is smaller than n naught, the algorithm does not recurse. It directly returns the answer. That's why t event for that recurrence is theta of 1 for, right? It doesn't literally mean exactly one step. Instead, there's some minimum time constant is greater than 0 because even the tiniest input still requires some work. A procedure, yeah, there's still some work that's being done, but it's just not bounded by the asymptotic worst case running time, right? Two positive constants. Okay. Hey Austin, how's it going, man? Welcome in. Welcome into the afternoon Saturday stream here, early stream. I'll probably do a late night coding session around maybe 9 p.m. PST or something like that. Where we'll work on maybe the project or write some sort of script or do something, get some practice with some more programming. Actually, write programming. Maybe work on some of these problems actually from the previous chapters. Actually implement a merge sort and a insertion sort algorithm into our notes and stuff. That would be some good practice, I think, to take on tonight potentially. All right. Conventions for recurrences. We adopt the following convention. Whenever a recurrence is stated without an explicit base case, we assume that the recurrence is algorithmic. That means you're free to pick any sufficiently large threshold constant, n naught, for the range of base cases where t of n, the recurrence, is equal to theta of 1. Interestingly, the asymptotic solutions of the most algorithmic recurrences you're likely to see when analyzing algorithms don't depend on the choice of threshold constant as long as it's large enough to make the recurrence well defined. Asymptotic solutions of algorithms divide and conquer recurrences also don't tend to change when we drop any floors or ceilings in a recurrence defined on the integers to convert it to a recurrence defined on the reals. Section 4.7 gives a sufficient condition for ignoring floors and ceilings that applies to most of the divide and conquer recurrences you're likely to see. Consequently, we'll frequently state algorithmic recurrences without floors and ceilings. Doing so generally simplifies the statement of the recurrences as well as any math that we do with them. You may sometimes see recurrences that are not equations, but rather inequalities, such as the recurrence t of n is less than or equal to 2t of n divided by 2 plus o theta of n. Because such a recurrence states only an upper bound on t of n, we express its solution using O notation rather than theta notation. Similarly, if the inequality is reversed to t of n is greater than or equal to the 2 times t of n divided by 2 plus theta of n, because the recurrence only gives a lower bound on t, then we use omega notation in its solution. Okay. Right, if you're having some bounding happening, you can't go any faster than this, or you can't, this is how fast it can go, and this is the worst case, and this is the best case. Divide and conquer and recurrences. This chapter illustrates the divide and conquer method by presenting and using recurrences to analyze two divide and conquer algorithms for multiplying n times n matrices. Section 4.1 presents a simple divide and conquer algorithm that solves a matrix multiplication problem of size n by breaking into 4 subproblems of size n divided by 2, which it then solves recursively. The running time for the algorithm can be characterized by the recurrence of t of n equals to 8 times t of n divided by 2 plus theta of 1, which turns out to have a solution of t of n is equal to theta of n cubed. Although the divide and conquer algorithm is no faster than the straightforward method that uses a triply nested loop, it leads to an asymptotically faster divide and conquer algorithm due to the V-Strassen, which we'll explore in section 4.2. Strassen's remarkable algorithm divides a problem of size n into 7 subproblems of size n over 2, which it solves recursively. The running time of Strassen's algorithm can be described by the recurrence t of n equals to 7 times t of n over 2 plus theta n squared, which has the solution of t of n equals to theta of n to the power of log 7, which is equal to big O of n to the power of 2.81. Strassen's algorithm beats the straightforward looping method asymptotically. These two divide and conquer algorithms both break a problem of size n into several subproblems of size n divided by 2, or n over 2. Although it is common when using divide and conquer for all the subproblems to have the same size, that isn't always the case. Sometimes it's productive to divide a problem of size n into subproblems of different sizes, and then the recurrence describing the running time reflects the irregularity. For example, consider a divide and conquer algorithm that divides a subproblem of size n into one subproblem of size n over 3 and another size of 2n over 3, taking theta of n time to divide the problem and combine the solutions to the subproblem. Then the algorithm's running time can be described by the recurrence t of n is equal to t of n over 3 plus t of 2n over 3 plus theta of n, which turns out to have the solution t of n equals to theta n log n. We'll see an algorithm in chapter 9 that solves a problem of size n by recursively solving a subproblem of size n over 5 and another of size 7n over 10, taking theta n time for the divide and combine steps. Its performance satisfies the recurrence t of n is equal to t of n over 5 plus t of 7n over 10 plus theta n, which has solution t of n is equal to theta n. Although divide and conquer algorithms usually create subproblems with size of constant fraction of the Although divide and conquer algorithms usually create subproblems with sizes of constant fraction of this original problem size, that's not always the case. For example, a recursive version of linear search, see exercise 2.1-4, creates just one subproblem with one element less than the original problem. Each recursive call takes constant time, plus the time to recursively solve a subproblem with one less element, leading to the recurrence. T of n is equal to t of n less than 1 plus theta of 1, which has a solution t of n equal to theta of n. Nevertheless, the vast majority of efficient divide and conquer algorithms solve subproblems that are a constant fraction of the size of the original problem, which is where we'll focus our efforts. Cool. That was a lot of information there. It kind of was a lot of preluding to future chapters and some potential algorithms we'll see, but it just kind of wanted to show you that you don't always have to divide a subproblem using a divide and conquer algorithm or process into equal parts. There is some advantages and potentially time savings asymptotically, by dividing into, say, uneven groupings and then combining at the end in that way somehow. So we're going to get to those eventually, but it didn't get those into too much detail at this moment. Take another drink here. How's your guys' Saturday so far? What you guys been up to? If you guys are here, part of the early stream, feel free, if you guys wouldn't mind leaving a like, and if you guys are new, my name is Michael. Thanks so much for joining me here. We're reading Introduction to Algorithms, Chapter 4, Divide and Conquer. We're learning a lot of great stuff on recursion, which is always good, as recursion is kind of more of a struggle for me, as self-taught in this field here. Solving recurrences. After learning about divide and conquer algorithms for matrix multiplication in section 4.1 and 4.2, we'll explore several mathematical tools for solving recurrences. That is, for obtaining asymptotic theta, O, and omega bounds on their solutions. We want simple to use tools that can handle the most common occurring situations. But we also want general tools that work perhaps with a little more effort for less common cases. This chapter offers 4 methods for solving recurrences. Okay, here we go. So I'm going to do a heading here. Oh, my laundry finished here. I gotta go swap my laundry. We'll do 4 methods for solving recurrences. Number 1, the substitution method. Okay. In the substitution method, section 4.3, you guess the form of a bound and then use mathematical induction to prove your guess correct and solve for constants. This method is perhaps the most robust method for solving recurrences, but it also requires you to make a good guess and to produce an inductive proof. Okay. 2 is recursion tree method. The recursion tree method, section 4.4, models the recurrence as a tree whose nodes represent the costs incurred at various levels of the recursion. To solve the recurrence, you determine the costs at each level and add them up, perhaps using techniques for bounding summations from section 8.2. Even if you don't use this method to formally prove a bound, it can be helpful in guessing the form of the bound for use in the substitution method. 3, master method. The master method, section 4.5 and 4.6, is the easiest method when it applies. It provides bounds for recurrences of the form T of n is equal to A times T of n over B plus F of n, where A is greater than 0 and B is greater than 1, are constants, and F of n is given driving function. F of n is a given driving function. This type of recurrence tends to arise more frequently in the study of algorithms than any other. It characterizes a divide and conquer algorithm that creates A subproblems, of each of which is 1 over B times the size of the original problem, for using F of n time for the divide and combine steps. To apply the master method, you need to memorize 3 cases, but once you do, you can easily determine the asymptotic bounds on running times for many divide and conquer algorithms. Okay, so this one's kind of not that hard to follow here. You basically have some recurrent occurring, right? You have this recurrence instance, and then you can continue on with the recurrence instance by dividing the subproblem over b, which is some constant greater than 1, because you can't divide by 0. It's undefined. So you divide the constant by some value to reduce into a subproblem, and you're doing that a times, right? You're doing that some constant a amount of times. So that's just the amount of recurrences occurring, and this is the amount of like the size of the recurrence, right? And then this is, the operations are, I guess, or whatever, the driving function that occurs, at each step to, determine something, or maybe there's some sort of operations that happen, or whatever. I'm not exactly sure what this driving function does. They didn't give too much detail on it, but I'm assuming that this is just some sort of operational functions that occur on the data at these certain recurrence levels. Number 4 The Akrabazi method. Section 4.7 is a general method for solving divide and conquer recurrences. Although it involves calculus, it can be used to attack more complicated recurrences than those addressed by the master method. Okay. 4.1, multiplying square matrices. We can use the divide and conquer method to multiply square matrices. Pardon me. If you've seen matrices before, then you've probably known how to multiply them. Otherwise, you should read section D.1. Let A equal to A of I, K, and B equal to B of J, K. B square n times n matrices. The matrix product C equals to A times B is also an n by n matrice, where for I and J is equal to 1, where for I and J are equal to 1, 2, all the way up to some value n, and the ij entry of C is given by C of ij is equal to the sum of all values, indices 1 through n, of the matrix A, I sub k, sub ik, times B sub kj, right? So this is kind of just fancy math notation for saying that you have some two matrices of size n by n, equal size. You're going to multiply them together to get some matrix C, which is n by n. And you can denote the index result of ij as an entry of C, which is given as just A at that entry of that same cell times B of that same cell. Generally, we'll assume that the matrices are dense, meaning that the most gosh, I cannot read. Generally, we'll assume that the matrices are dense, meaning that most of the n squared entries are not zero, as opposed to sparse, where most of the n squared entries are zero, and the non-zero entries can be stored more compactly than in an n by n array. Computing the matrix C requires computing n squared matrix entries. Oh my goodness. Computing the matrix C requires computing n squared matrix entries, each of which is the sum of n pairwise products of input elements from A and B. The matrix multiply procedure implements this strategy in a straightforward manner, and it generalizes the problem slightly. It takes as input 3 n by n matrices A, B, and C, and it adds up the matrix products A times B to C, storing the result in C. Thus, it computes C is equal to C plus A times B. Thus, instead of just C equals A times B, if only the product A times B is needed. Just initialize all n squared entries of C to 0 before calling the procedure, which takes an additional theta of n squared time. We'll see the cost of matrix multiplication asymptotically dominates this initialization cost. So matrix multiply A, B, C, n. For I equals to 1 to n, for j equals 1 to n, and for k equals 1 to n, we're going to have C equals to C plus, C index of I and j equals to C of index in I and j, the current value at that resulting matrix, plus the multiplication of the same cell represented in A times the same cell value represented in B. The pseudocode for matrix multiply works as follows. The for loop of lines 1 through 4 computes the entries for each row I within a given row Ji for the, oh my gosh, the for loop of the lines 1 through 4 computes the entries of each row I and within a given row I. The for loop of lines 2 through 4 computes each of the entries C of I, J for each column J. Each iteration of the for loop of lines 3 through 4 adds in one more term of equation 4.1. Because each of the triply nested for loops runs for exactly n iterations and each execution of line 4 takes constant time, the matrix multiply procedure operates in theta of n cubed time. Even if we add in the theta n squared time for initializing C to 0, the running time is still theta n cubed. So it kind of just went over basically triply nested for loops here and how each of them are iterating all the way up through n and doing some computation. So even if we initially set all the values within C to 0, right, it's still bounded by this cubed operation in the worst case. Not in the worst case, but always, right? It will always have to do that because it's theta of n cubed. A simple divide and conquer algorithm. Let's see how to compute the matrix product A times B using divide and conquer for n greater than 1. The divide step partitions the n by n matrices into 4 n over 2 by n over 2 submatrices. We'll assume that n is an exact power of 2 so that as the algorithm recurses, we are guaranteed that the submatrix dimensions are integers. Exercise 4.1-1 asks you to relax this assumption. As with matrix multiply, we'll actually compute C equals to C plus A times B. But to simplify the math behind the algorithm, let's assume that C has been initialized to the 0 matrix, so that we are indeed computing C equals to A times B. The divide step views each of the n by n matrices C, B. The divide step views each of the n by n matrices A, B, and C as 4 n over 2 by n over 2 submatrices. So each matrix n by n was divided into 4 n over 2 by n over 2 submatrices. So the product can be written as this, which you can expand this out to equal to this, which corresponds to the equations of C11 equals to A11 times B11 plus A12 times B21. Okay. Equations 4.5 through 4.8 involve 8 n over 2 by n over 2 multiplications and 4 additions of n over 2 by n over 2 submatrices. Right. As we look to transform these equations to an algorithm that can be described with pseudocode or even implemented for real, there are two common approaches for implementing the matrix partitioning. One strategy is to allocate temporary storage to hold matrix A's 4 submatrices A11, A12, A21, and A22, and B's 4 submatrices A11, B12, B21, and B22. Then copy each element in A and B to its corresponding location in the appropriate submatrix. After the recursive conquer step, copy the elements in each of C's 4 submatrices, C11, C12, C21, and C22, to their corresponding locations in C. This approach takes theta n squared time since 3 times n squared elements are copied. The second approach uses index calculations and is faster and more practical. A submatrix can be specified within a matrix by indicating where within the matrix the submatrix lies without touching any matrix elements. Partitioning a matrix or recursively a submatrix only involves arithmetic on this location information, which has constant size independent of the size of the matrix. Changes to the submatrix elements update the original matrix since they copy the same storage. Going forward, we'll assume that index calculations are used and that partitioning can be performed in theta of 1 time. Exercise 4.1-3 asks you to show what it makes. Exercise 4.1-3 asks you to show that it makes no difference to the overall asymptotic running time of the matrix multiplication. However, whether the partitioning of matrix uses the first method of copying or the second method of index calculation. But for other divide and conquer matrix calculations, such as matrix addition, it can make a difference, as exercise 4.1-4 asks you to show. The procedure, matrix multiplication recursively, uses equations 4.5 through 4.8 to implement a divide and conquer strategy for 4-square matrix multiplication. Like matrix multiply, the procedure matrix multiply recursive computes C equals to C plus A times B, since, if necessary, C can be initialized to 0 before the procedure is called to compute only C equals to A times B. So matrix multiply recursive given these parameters. If n equals 1, we've reached our base case. So we compute a C equals to C plus A times B, and we return. We set that value, right? Now we divide. Partition A, B, and C into n over 2 by n over 2 submatrices, right? Now we conquer. Now we multiply, use the recursive call on these new partitions. As we walk through the pseudocode, we'll derive a recurrence to characterize its running time. Let T of n be the worst case time to multiply 2 n by n matrices using this procedure. In the base case, when n equals 1, line 3 performs just the one scalar multiplication and one addition, which means that T of 1 equals to theta of 1. As in our convention for constant base cases, we can omit the base case in the statement of the recurrence. The recursive case occurs when n is greater than 1. As discussed, we'll use index calculations to partition the matrices in line 6 taking theta of 1 time. Lines 8 through 15 recursively call matrix multiply recursive a total of 8 times. The first 4 recursive calls compute the first terms of equations 4.5 and 4.8, and the subsequent 4 recursive calls compute and add in the second terms. Each recursive call adds the product of a submatrix of A and a submatrix of B to the appropriate submatrix of C in place, thanks to index calculations. Because each recursive call multiplies 2 n over 2 by n over 2 matrices, thereby contributing to T of n over 2 to the overall running time. The time taken by all 8 recursive calls is 8 times T of n over 2. There is no combined step because the matrix C is updated in place. The total time for the recursive case, therefore, is the sum of the partitioning time and the time for all recursive calls, or theta of 1 plus 8 times T of n over 2. Thus, omitting the statement of the recursive base case, a recurrence for the running time of matrix multiply recursive is T of n equals to 8T of n over 2 plus theta of 1. As we'll see from the master method in section 4.5, recurrence 4.9 has the solution T of n equals to theta n cubed, which means that it has the same asymptotic running time as a straightforward matrix multiply procedure. Why is the theta n cubed solution to the recurrence much larger than the theta n log n solution to the merge sort recurrence in 2.3 on page 41? After all, the recurrence for merge sort contains a theta n term, whereas the recurrence for recursive matrix multiplication contains only a theta of 1 term. Let's think about what the recurrence tree for recurrence 4.9 would look like as compared with the recurrence tree for merge sort illustrated in figure 4.5 on page 43. The factor of 2 in the merge sort recurrence determines how many children each tree node has, which in turn determines how many terms contribute to the Okay, hold on, I gotta restart this one. Let's think about what the recurrence tree for the recurrence. Oh my gosh, sorry you guys. Let's think of. We're reaching that level. I'm getting cotton mouth. My tongue is getting sore. Pause. Let's think about what the recursion tree for recurrence 4.9 would look like as compared with the recursion tree for merge sort illustrated in figure 2.5 on page 43. The factor of 2 in the merge sort recurrence determines how many children each tree node has, which in turn determines how many terms contribute to the sum at each level of the tree. In comparison, for the recurrence 4.9 for matrix multiply recursive, each internal node in the recursion tree has 8 children, not 2, leading to a bushier recurrence tree which has more leaves despite the fact that the internal nodes are each much smaller. Consequently, the solution to recurrence 4.9 grows much more quickly than the solution to recurrence 2.3, which is born out of the actual solutions theta of n cubed versus theta n log n. Cool, so they give us some exercises here. So that was the end of 4.1, multiply matrices. I didn't really take any notes there. So let's see if I can go back through really quickly and take some notes. So we'll say dense matrix, so this says most of the entries, most of the n squared entries are not 0. Does that? No. So how do you, let me see here, let me say superscript in markdown. So soup with the HTML tag. Does it have a closing tag? Yeah. Okay. And then soup and sub and sub. Are dense, meaning most of the n squared entries are not 0. And then you have a sparse matrix. Most of the n entries are 0. And the non-zero entries can be stored more compactly than in an n by n array. Okay. So what does this actually like mean? Can you break the section down? So a sparse matrix definition, most of the n squared entries are 0. Example, a 1000 by 1000 entries has 10 to the 6 entries, where only about 1% are non-zero. Matrix. Would the indices be saved in an object with the val? Exactly. If you only save the non-zero values, you also need to remember where they live in the n by n grid. This is why sparse matrix formats always store indices plus values together. So you coordinate a list of a CO format, a coordinated list. So you have tuples, a list of tuples, where we have a values, row, column, and then the value. Okay. So what does it mean by n squared, though? When we say n by n a matrix, that has n rows and n columns, so it's n squared total number of entries. A 3 by 3 matrix would have 9 entries, would have 1,000,000 entries for 1,000. Why n squared? So most of those n squared, okay, so it's just a representation of saying the resulting factor of the n by n, all of the entries. Okay, got you. So this means, this is saying most of the n are not 0, meaning we need to save, hold on, I'll be barking. I'll be barking. What's going on? Meaning we need to save. What the dog doing? Hold on, we'll let her get that out of her system. Meaning we do need to save most, if not all, of the data of n squared entries within the n by n array, right? Now a sparse, so we'll say like we can package this data together in a tuple within an array for each, no, so hold on, we won't do that one here. We would say that's for sparse. So, meaning, if a majority of the data entries, of the n squared data entries, within the n by n array, meaning if a majority are 0, we do not need to store them. We only care about non-zero values. We would need to save reference to the locations, however, of the non-zero values to place them back when reconstructing. Something like this. So a dense matrix, most of the n squared entries are non-zero, meaning we need to store nearly all n squared entries directly in the n by n array. A sparse matrix, most of the n squared entries are zero, so the non-zero entries can be stored more compactly than in the n by n array. If the majority of the n squared entries are zero, we only store the non-zero values. However, we must also store location indices. I'll copy that. That looks good. So I'm going to keep some formatting here. I like how it has this. Conquer, combine, base case, the definition, so recursive case, recurrence, for methods, method. Okay. A powerful and efficient algorithms with 3 steps. Cool. So then I'm going to take matrix multiplier. Grab this. Oops. Come on, give me a better pick. Better pick than that. Let's go here and grab a better pick. If you guys would like access to these notes, they're on my GitHub. They're great little Spark notes, basically, of the chapter, and kind of give you all the meat of what I read over and what I kind of the important stuff, I think. And obviously you want to go through yourself and read it, or watch the video back and listen to it, the chopped up versions, right? But you guys can get access to my notes here on my GitHub. I push them up in the description below. Cool. This one was a loop. This one was recursive. Right. All right, sweet. So we'll pick back up on 4.2 next time we get back into the reading here. Strassen's algorithm for matrix multiplication. Okay, we'll go get add here. That started 4. All right, sweet. Nice. Awesome, you guys. Awesome. Stromy. As you work full time and also learn programming, do you still have time for any other activities on the side? uh, Honestly, dude, not really. I kind of feel bad. I probably should do more and stuff. You know, I used to do a lot more like skateboarding, and things like that, but I just kind of realized that a lot of value and I guess you know I don't know. I've really tried to figure out what's the best way I can optimize my time for. I don't know. I think I need to stop with this whole return on investment mindset, I guess, and just do things just to have fun and live life. But I've been on this like investment return on investment kick to where like, oh, I have to spend my time doing things that bring an actual return for something, and whereas the return can be just to relax. But anyways, no, not really. I honestly I but in the time that I don't spend either streaming, editing videos or going to work or hanging out with my girlfriend and my dog, I usually spend honestly just sleeping, and because I getting caught up on sleep, so I can keep going. But that's kind of the truth of it. I don't really go out much, or besides the grocery store, I guess. Maybe the park or so on the weekends. Okay, cool. So that was a good chunk of reading we got done there. We read all of the introduction to chapter 4 here regarding divide and conquer, introducing divide and conquer, recurrences, algorithmic recurrences, the kind of the conventions for it, and what the notations for T of n, or these recurrences, which are just you know cases of the value which we identified as n naught, which is some value within our data set to where we actually can invoke recurrences on to where a base case will no longer be met. Just think of it to where we reach some value of n, where we can invoke recurrences to then reduce n down, right, by creating subproblems, divide, conquering on those subproblems, performing some sort of operations, um, and then combining for the subproblems into a solution, right? So it was really kind of cool to actually get some more solidified breakdown about recursion, because honestly, recursion is a little bit more of a difficult topic for me. I don't know, it just hasn't quite stuck yet in an actual coding, but the idea of it is there. But definitely need to get some practice. I want to really go back through, I think maybe tonight, when I come back on for our after hour stream, and maybe just go over some of the problems in chapter 3 and chapter 4 here, and as well as chapter 2. We do need to go back through and complete some of these exercise problems, along with our notes. So we do need to kind of do some polishing and going back through. But anyhow, this is a fun little hour. I wanted to kind of jump on and get into do some reading, as this chapter is pretty long and we probably will need to break it up into multiple sections. So we are on 4.2, Strasson's algorithm for multiplying matrix multiplication, which is on page 85, 86. And we need to go down to, I believe, here, 118. So about like 40 pages or so. It's a pretty long chapter. So that's why I kind of wanted to break it down. Anywho, I will see you guys later tonight, this evening. So please join my Discord if you would like a announcement for when I'm hopping on, so you can make sure you be there for just a live coding session, chill out, where we'll watch some videos, probably Primogen, more of those kind of horror story programming videos, and get some work done on our project. Start designing. I think it might be easier for us to start designing the product page of our site rather than the home hero page, because we still need to do some designing for that. Whereas the product page, we kind of just need to lay out some data. So I think it'd be better for us to maybe switch our focus over to that. And yeah, so we'll work on that tonight. So make sure you guys are here. but I'll see you guys in a few hours. Thank you guys so much for joining me for this little reading session where we kind of did a little warm up and got kind of going for the day.